All right. Hello, and thank you for reviewing this briefing. Today, we're going to be comparing conventional sheet metal forming with an emerging advanced technology called roboforming. This is more generally known as incremental sheet forming. So the purpose of our proposal today is that we're preparing to invest in this new sheet metal forming line, and we need to decide between a proven conventional process or a newer, highly flexible alternative. We'll walk through the capabilities, advantages, limitations, costs, and give a manufacturing readiness level assessment with a clear recommendation by the end. The goal is to evaluate and determine whether roboforming is mature enough for adoption in our manufacturing line.
So we'll only touch briefly on conventional sheet metal forming since this is already core to our operations. It forms metal by using dies and presses, and it's extremely fast. You put a sheet of metal in, the die makes a shape, and you put it out and you have one part, and it only takes a few seconds. So these parts are consistent and dimensionally stable and come at a very low cost per unit. The big downside is the high initial tooling cost of the dies, ranging from $15,000 for smaller dies to over $250K for automotive manufacturing. Roboforming, on the other hand, is fundamentally different. Instead of using a fixed die, it uses two coordinated robot arms to deform a sheet by pinching between two tools called effectors. These effectors trace out the desired shape, and the purpose of this is to enable rapid prototyping and customizable parts, comparable to 3D printing over injection molding. Currently, the only company demonstrating near production capability is Machina Labs, though incremental forming has been studied for years in research settings. So here's a quick video to demonstrate how roboforming works in a real production setting. Isn't that cool? So the capabilities of conventional forming is that it excels in high volume production and dimensional repeatability. Roboforming, on the other hand, as you see, is more flexible. The system can generate concave and convex forms in the same cycle and follow complex toolpaths. CAM is linked with FEA to ensure structural integrity during forming, and real-time force sensing allows closed-loop corrections to eliminate geometric errors.
So now let's look at some of the advantages. We know sheet metal forming's advantages quite well since we use it a lot. It has a high production rate, low part costs, and extremely mature processes. It also, as we know today, hasn't changed in decades. Roboforming, on the other hand, is ideal for prototyping, low volume production, or customization. Because the deformation is incremental, there's almost no spring back as opposed to sheet metal forming. On top of this, we get more complex geometries. The maintenance of roboforming is also simpler. Robot arms are standardized industrial hardware nowadays, and this means there's widely available service resources. The only additional physical tools are the end effectors, and there's much lower barrier of entry due to these reasons for roboforming. Finally, there's a current push to make the systems deployable almost anywhere a shipping container can be. Now, this enables roboforming to fill in gaps in the supply chain. Next, now that we talked about the advantages, it's important to note the limitations. So again, with sheet metal forming, the biggest limitation is that high initial cost and the lack of flexibility. A $100,000 die can make only one part, or maybe a few parts at a time. However, there's also the biggest limitation for roboforming, which is speed. It is orders of magnitude slower than stamping. Stamping only takes a few seconds to make one part or even a few parts at the same time, whereas roboforming can take hours to make the same part. The industrial base for roboforming is also very small. Another limiting factor is the development of the software for roboforming. It requires advanced toolpathing, geometry scanners, neural network type models, and a bunch of other complex software to accurately form the metal. Only Machina Labs is highly publicized, and without any evidence of true production yet, even though there's a lot of research, we just can't say whether this technology is able to be used.
So getting more into the details on cost, the contrast is clear. Conventional forming has a high upfront investment. Dies, presses, and automation are all very expensive. But once production ramps up, the cost per part becomes extremely cheap. Roboforming is kind of the opposite. It has a lower barrier to entry, relatively, and since you mainly invest in robot arm sensors, software, and fixturing. However, the process is so slow that the cost and time per part is not competitive with higher volumes. It's only more effective in lower volumes or when parts need to be customized. So for high volume manufacturing, roboforming is simply not economical. So in assessing the manufacturing readiness of this technology, roboforming appears to be at approximately level 5. Machina Labs has produced custom automotive panels, including a truck hood, in a production relevant environment. The digital controls, inline sensing, and modeling tools are strong indicators of maturing technology. However, it lacks the data needed to reach level 6 or 7, which includes long-term production yields, validated cycle times, supplier quality programs, workforce training models, high volume reliability, and cost modeling over thousands of parts.
All right, so now that we've gone over a lot of the important information about roboforming, it's also important to address the bias with where we got our information about this research. So most commercially relevant information comes from the Machina Labs themselves, who claim that they can do fighter jet repairs from years and make it happen in days, among other things that they've not yet proven. Videos by YouTubers such as Hard Reset and Smarter Every Day are well detailed, but they can be slightly misleading to the actual capabilities of this technology. The cost and specifications we looked at from robotic vendors are also accompanied by heavily biased articles to sell their own products. So independent studies exist, but production scale studies are limited. And to properly assess the readiness, we really need more people using this technology so they can give honest feedback of the process and its results. So now let's talk about the investment worthiness. With all this in mind, is it worth investing? We believe that for high volume production, the answer today is no. Production rate and cost per part cannot compete with the conventional forming methods. Roboforming is valuable in small volumes due to its lower initial cost. It enables rapid prototyping, short-run production, aftermarket parts, and one-off geometries. And it's just much like the early days of 3D printing. It's still expensive, it's slow, and the quality of parts can't always compete with the traditional methods, but with further commercialization, we could possibly see a prototyping revolution like that with 3D printing. It took over 20 years for 3D printing to go from niche commercial uses such as medical implants and jewelry to the popularity that we see today. It's still in that niche stage, and we'll likely see this development with better softwares and production rates in the next few years. These are all what if still, though, so until that reaches that manufacturing readiness level of 6 or 7, this technology needs to be reevaluated at a later date until it can meet our cost requirements.
So, in summary, conventional sheet metal forming remains the only viable choice for high volume production due to its unmatched speed and cost per part. Roboforming offers additional flexibility, but it lacks the maturity and reliability that we need to know before implementing it into our full-scale operations. Our recommendation then is to invest in roboforming as a supplementary capability for prototyping, customized parts, and low volume production, while maintaining sheet metal forming as the background of high volume manufacturing. So we should reassess roboforming when the technology reaches a manufacturing readiness level of 7 or higher, and at that point we can maybe implement it into our daily operations.
Thank you.
Thank you.